there's some chance that I'll need to end class a few minutes early in any case. So there's a bunch of new administrative stuff on the course webpage. So the first thing is there is a homework 11. It's not going to be graded. I'm sorry, there was a question?
On your distribute ISIS, it says end of class on Thursday, April 28th. Please come to the last 15 minutes of Tuesday's lecture.
Well, yeah, you should please come to the last 15 minutes, but yeah. Sorry. I'll fix that. Please do come to the last 15 minutes of Thursday's lecture. Yeah, I think that was just a copy and paste from last semester. Okay, so there's a homework 11. It's not going to be graded, but it's practice. Think of it as a set of practice problems at the level of difficulty that we would normally have for a homework assignment. For the approximation stuff that we've been doing Thursday, today, and this coming Thursday. Some of that material may appear on the final exam, but keep in mind that the usual constraints of exam problems apply. That on the homework, we're assuming that you have a week with a group of students and the internet, and on an exam, we assume you have 30 minutes and a piece of paper. On Thursday, 2 days from now, I'll distribute ISIS forms at the last 15 minutes of class. Please try to come, even if you're if you normally don't. If you have friends who've already dropped the class, please encourage them to come, if only for the last 15 minutes, to tell me why. It's really very important to me personally and to the department to get your honest feedback on how the course is going. I mean, the same is true for every other class that you're taking. And this is really your primary opportunity to give me direct, brutally honest feedback on what's gone well and what hasn't. Next Tuesday, a week from now, there won't be an actual lecture. I will answer questions, and by questions I mean almost any question. If you are used to Reddit, you can think of this as an AMA. In particular, you should not restrict your questions next week to questions about the final exam, although I'm happy to answer those as well, because I am trying to arrange for a review session on Thursday, the day before the actual final. The final's on Friday evening. We're in 100 Gregory Hall, all in one room. Everything is the same as the midterms, except there will be 6 questions instead of 4. You have 3 hours instead of 2, and you can bring in 2 sheets of paper instead of 1. Everything is going to be in scope, but when I say everything, I mean basically everything that you've never had that you've had homework about. So we're not really going to be talking about, for example, min-cost flows. We're not going to be talking about the strong exponential time hypothesis. We might have a simple question about approximation algorithms, but it'll have to be simple. I still need to update the 10-point rubrics for things like NP hardness proofs. There will be a conflict exam. If you, for some reason, need to take the conflict exam, please fill out this form as soon as possible, but definitely no later than Tuesday so that I can actually schedule the room. Once we know when and where the exam is going to be, you can, which we'll hopefully announce next Wednesday, you can continue to register, but I need to know by the end of the day, Thursday, whether you're going to show up for the regular Friday exam or if you plan to take the conflict. People who need a conflict basically means people who have another exam at exactly the same time, Friday at 7 p.m., or who have 3 exams in 24 hours, which means Friday at 8 a.m., Friday at 1:30 p.m., and Friday at 7 p.m. There aren't any off exams Saturday or Sunday. So Monday exams, I don't think, qualify you for an overflow. There is an option in the registration form when I ask for, what everybody's conflict is, whether people would be willing to take the conflict exam on Saturday. There are not regular exams on Saturday. I'm throwing this out as an option just because maybe you'd rather do that than and get it all over with. But we're not actually going to schedule a conflict exam unless everybody who needs a conflict is willing to do it. Okay. Any other administrative questions about this stuff, about the exam? Yeah.
So you can still take the conflict even if you don't have any conflict.
That's right. Once the conflict is there, I need to have a rough idea of how many people are going to show up in time to schedule the room. My guess is that the conflict is probably going to be Monday after the regular exam rather than earlier. So we'll still have time to do it. But what I don't want to happen is for somebody to come into the regular exam and then say, oh, I'm going to take the conflict. Okay. So all that's on the web. So on last Thursday, we started talking about approximation algorithms. The basic idea behind an approximation algorithm is that it may be prohibitively expensive to compute an optimal solution to certain kinds of problems, either because the problem is NP-hard or because the running time of the best known optimal algorithm, the best known algorithm to compute the optimal solution, even if it's polynomial, because of the size of the data that you're having to compute this on, that polynomial's too big to actually be realistic. So the idea is behind an approximation algorithm. Sorry, let me make that a little bit smaller. An approximation algorithm. In particular, actually, let me just start over here. An alpha approximation algorithm. What this means is that it computes a solution A of x for input x, such that depending on whether the problem is a maximization problem or a minimization problem, one of these two is going to apply. Okay, so what you imagine is you have your algorithm A that computes, for example, the length, tries to compute the length of the shortest traveling salesman tour in a graph. Now, the optimal solution, that's NP-hard, but we imagine that somehow, for purposes of analysis, we know what that is. That's optivex. And we take the ratio between the output of our algorithm and the output of the optimal algorithm. Right? So, for example, if I say, alpha is 1.5, that means an alpha approximation algorithm computes a solution that is at most 50% bigger than the optimal solution. Now, you can also have approximation algorithms for minimization problems. This is, when I say solution 50% bigger than optimal, I'm assuming something like TSP that's a minimization problem. But you might also have a maximization problem, like maximum independent set. And then alpha equals 1.5 means that I compute an independent set whose size is at least 2/3 the size of the true maximum independent set. This 2/3 is 1/3 alpha here, this approximation ratio, I'm going to just assume is always going to be stated in a form that's bigger than 1. Okay. So what we talked about on Thursday was this minimum make-span scheduling algorithm, where essentially we argued that if I have a greedy algorithm where as I receive a job, I put it onto I assign it to the processor that has the earliest finishing time for the jobs that it's already scheduled. This was a two approximation algorithm. And if I first sort the algorithms in, the jobs in decreasing order, then the approximation ratio improves from 2 to 3 halves. When we talk about a 3 halves approximation, the setting alpha to 3 halves, notice that that's defined in terms of an inequality. So we didn't show this in class because it requires a bit more technical expertise than I'm prepared to actually pretend to have. The approximation ratio for that algorithm is actually not 3 halves, it's 4/3. So the approximation ratio that you can derive for a given algorithm is kind of like an upper bound on the running time of an algorithm. It's perfectly fine to say merge sort runs in big O of n cubed time. It's true. It runs in big O of n cubed time. It's not the strongest statement you can make, but it's better than saying that it runs in 2 to the n time. Same thing here, it's sorting plus greedy. Because it's an instance of the greedy algorithm, I know it has an approximation ratio of at most 2. But with better analysis, you can show it's at most 3 halves, which we did. And with better analysis still, we can get 4/3, which is actually the right answer. For the most part, the kinds of analysis that we're going to see for other examples, the analysis, the first analysis that people try actually gives the right answer, just as it does for most of the time when we analyze algorithms. As long as we do it carefully, we're going to get the actual tightest bound we can get. And then the second thing we considered was the vertex cover problem. And there's a natural greedy heuristic. Right? We're trying to find the smallest set of vertices that we can that covers every edge of the input graph. And the natural greedy heuristic is you repeatedly choose the maximum degree vertex because that's the vertex that covers the most edges. This turns out to be a log n approximation algorithm where n is the number of vertices. And this is an example where that's the best you can do. This is an example where the approximation ratio alpha isn't a constant, but rather it's a function of the input size. As graphs get bigger and bigger, you can guarantee sort of worse and worse approximation ratios. But then at the end of class, after the video cutout, there's a really dumb algorithm that's actually quite a bit better than the greedy algorithm and moreover is trivial to analyze, which gives you a 2 approximation. So the basic algorithm, it looks like this. For all edges u and v, if u and v are both unmarked, mark them both. And then the set of marked vertices is the vertex cover that we return. Now, immediately people say, wait, no, why do you mark them both? You don't need to mark them both. You only need to mark one. Yeah, I only need to mark one. But remember that my goal here is not actually to find the smallest possible vertex cover. It's to find something good enough. Right? And the proof that this is a two-approximation algorithm is pretty simple. It says, well, there's an edge, UV. I've marked both of its endpoints. In the optimal vertex cover, I must have marked one of them. The end. So I marked two, optimal would mark at least one. And it turns out that, if you only try to mark one, that's really actually pretty bad. So if you imagine, I don't know why this is insisting on going into screensaver mode here. Let's try that corner. Think about a tree that looks like this. Okay. So let's say I decide I'm only going to mark one of the two. So I'm going to look at, say this edge, and okay, I'll mark this one. Then I look at the next edge, I mark this one. I look at the next edge, I mark this one. I look at the next edge, I mark this one. Right, because you haven't specified which one to mark, you're going to end up doing something really stupid. You're going to mark all the leaves when the smallest vertex cover in this case is just the one vertex in the middle. But if I do the stupid thing and just say, okay, let's mark the thing in the middle and the thing on the end, then I'm only off by a factor of 2. Now you could say, well, obviously you should mark whichever endpoint has the higher degree, but then you're back into doing the greedy algorithm. And again, a more complicated argument shows that the approximation ratio still degrades from 2 back down to log n. Right. So what I want to show you today is very quickly to sketch a proof of this log n, because the two approximation algorithm is really good, and moreover, it's the best approximation algorithm we know for vertex cover. We don't know of a 1.99999 approximation algorithm for vertex cover. But for generalizations of vertex cover, the log n approximation algorithm actually generalizes in a nicer way than the two approximation algorithm. So let me describe a little bit more carefully what this this greedy vertex cover algorithm does. Okay. So for purposes of analysis, I'm going to add some extra steps to the algorithm. This is only so that I can refer to the current graph after I've executed I iterations of the main loop and the degree that I choose in the ith iteration of the main loop. I just want to give these various quantities that I'm going to use names so that I can refer to them by name later in the analysis. The actual algorithm is just going to be like 4 or 5 lines long. Okay. So I'm going to start by setting up the cover that I'm going to return. I'm going to initialize G0 to be the original graph G, and I'm going to set some index I to be 0. Then I'll have a while loop. While G sub I has an edge, meaning has at least one edge, I'll increment I. I'll let D sub I be the maximum degree of any vertex in the graph that fell out of the previous iteration. Right? And I'll let Vi be any vertex with that degree. And then I'm going to remove this vertex vi from the graph. I'm going to add vi to the vertex cover, and then I'm going to repeat. And at the end, I'm going to return whatever vertex cover I just created. Okay? So my pencil keeps running out of batteries, so I'm just going to talk for a second. All right, so here's the algorithm. Obviously, the indices here are not really particularly important as far as the real algorithm is concerned. I could just modify the original graph G as I go. This notation here means I'm deleting that vertex and all of its incident edges. This notation here means I'm adding that vertex to the set that I'm going to return. Okay. Okay, so there's my while loop. Okay, so I want to analyze this algorithm, but in order to do this, remember that the real goal here is to try to do something where if I'm trying to prove that a of x is less than alpha times opt of x, this is what I need to show that this is an alpha approximation algorithm. What I really want to do is, find something else that I can stick in the middle that's relatively easy to analyze. And the hard part here is the inequality on the right side of this thing. I need to show that opt of x is bigger than something, even though I don't actually know what the optimum thing is in advance, even though it's NP hard to compute the optimum thing in advance. So I'm going to approach this somewhat indirectly by trying to figure out something about this degree d sub I that I'm choosing in the ith iteration of this loop. Okay. And so the basic idea is let's look at the, let's let C star be the optimal, the minimum size vertex cover. And let's just start by looking at the original graph. So if I look at the degree, the sum of the degrees of the vertices in the original graph, but I only count the vertices in the optimal vertex cover. I don't know what the optimal vertex cover is, but I do know that it is a vertex cover, which means every edge is going to have at least one of its endpoints in C star. And what that implies is that if I sum up the degrees, this is going to be at least the number of edges in G. Right? So, in fact, what it's really going to be is equal to the number of edges in G plus the number of edges where both endpoints are marked. Right? So I count each edge that's marked only once, and I count each edge that's marked twice. That's bigger than counting every edge once. Okay. But on the other hand, this means that if I take the average degree among all the nodes in C star, right? So the average degree of V over all V in C star, this is at least the number of edges in the graph divided by opt. Okay. Notice now that this inequality is a lower bound on opt. This is saying opt is at least E over something. Right? So it's the right form to be deriving a lower bound. On the other hand, the maximum degree among all vertices is at least the average of the degrees of some subset of vertices. So what this says is the degree of the very first vertex that I pick out, the maximum degree vertex, that degree is going to be at least the number of edges in the graph divided by however many vertices there are in the minimum vertex cover. And more generally, this argument is going to imply that the ith degree that I choose is going to be at least the number of edges in the graph left behind at the previous iteration divided by opt. Okay? Same opt. In each case, I can walk through the argument by saying, let's look at the vertices in the optimum vertex cover and look at their degrees in this graph G sub I minus 1. That optimum vertex cover of the original graph G is still a vertex cover of the smaller graph because it's smaller. There are fewer edges to it. So the argument's still going to go through. I'm not really using the fact that it's an optimal vertex cover anywhere in this argument. It's a vertex cover. Okay. On the other hand, I can also, now I'm going to do something really weird. I'm going to say, let's imagine that I run this algorithm not to completion, but I'm going to run the algorithm opt times. The main loop, I'm going to generate opt times, and I'm going to stop. So I'm going to greedily generate a number of vertices that is equal to the size of the smallest vertex cover. And I'm going to stop and ask, what does the graph look like from now on? But the thing to realize here is that I can, because the graph is shrinking from one iteration to the next, at every iteration, the degree that I choose, the degree of the vertices that I choose for the first opt iterations is greater than or equal to the number of edges in the graph that I end with after opt iterations, divided by opt. Okay, now this is a weird thing, but let me now do something weirder with this weird thing. Charge up the pencil. All right, so does everybody understand where this inequality is coming from? Not why in the world am I doing this, but do you believe that it's true? Okay. The why in the world is, it'll fall out in the end. The why is because math. So let me do something weird here. And the weird thing that I'm going to do, unfortunately, is I think I'm going to have to write with my finger for a moment. So wake up. Okay, sorry. Let's try that again. Today is April 26th. Okay, so I'm sorry? Well, yeah, probably. Let's, there's a setting. I'm sorry? Color? Stop using pencil. Okay, good. All right, so I apologize because I don't even have my crappy stencil here. The sum over all these degrees going from I equals 1 up to opt. Wow, that's awful.
I have a stylus you can use.
Okay, that might be helpful. Okay, I'll try both. It's nice and heavy. Good. This is at least, again, the sum from I equals
1 up to opt, of the number of edges in G opt divided by opt, but that's just equal to the number of edges in G opt. On the other hand, I can count the number of edges in G opt in a different way. The number of edges that are left over after opt iterations is the number of edges in the original graph minus all the edges that I deleted in intermediate iterations. So this is the number of edges in the original graph minus the sum over all I from 1 to opt of the number of edges that I deleted in the ith iteration. How many edges did I delete in the ith iteration? Di. Oh. So I have opt on this side and the sum on both sides. So what that means is that this sum of di is at least the number of edges in the graph divided by 2. So remember, I don't know what opt is. But what I can conclude from this analysis is that after I've found the first opt vertices, I haven't necessarily covered all of the edges of the graph, but I've covered at least half of the edges of the graph. Which means now, if I run this opt more times, again, I'll cover at least half of the edges of the graph again. And so I'll have a fourth of the edges left. And after opt more times, I'll have an eighth of the edges left. And so after, let's say, 2 times natural log of n times opt iterations, I mean, this is actually overkill. I don't think I need, after log n times opt iterations. The number of edges left is at most the number of edges in the original graph divided by 2 to the log n. Oh, okay, so I actually do need that. 2 to the log n, well, but this is less than 1. Right, so 2 to the 2 log n is the same as n squared. The number of edges in the graph is less than n squared. It's most n choose 2. So the number of edges that I have left after this many iterations is less than 1. But if I have a set of edges whose cardinality is less than 1, what is it? Good, everybody answered correctly. Nothing, right? It's the empty set. And so the number of iterations that I need to complete the algorithm is at most 2 log n times opt. But in every iteration, I mark 1 vertex. So the number of vertices that I mark with this greedy algorithm is at most 2 log n times opt. The end. All right, so the number of vertices that I actually output is at most 2 log n times opt. 3D. Okay. So you might remember a version of this kind of argument before. When we talked about maximum flow, we looked at this heuristic, which is find the augmenting path from S to T that carries the maximum amount of flow. And the basic argument underneath that analysis is, after a certain number of iterations, I've reduced the amount of flow that remains in the graph by at least a factor of 2. And then, well, you repeat that log n times, and you've reduced it down to something so small it has to be 0. Okay? Exactly the same idea here. Okay? Any questions about this? So the nice thing about this is that there's a more complicated problem called set cover, where instead of a set of vertices and a set of pairs of vertices called edges, you imagine you have a set of things, say the people in this room, and you have a collection of subsets. Everybody in this room that has an A in your last name. Everybody in this room that has a B in your last name. Everybody in this room has a C in your last name, and so forth. And instead of asking, how do I find the minimum number of vertices that cover every edge, you can say, can I find the minimum number of subsets that cover everybody? Okay, so if everybody raises their hand, well, this is easy. I only have one hand up. All right, fine. We'll go through the embarrassing thing. So I imagine, okay, everybody with an E in your last name, drop your hand. Everybody with a T in your last name, drop your hand. Everyone with an R in your last name, drop your hand. You have an X in your last name, drop your hand. Okay, now that's a set cover of size 4, because I picked up 4 letters, 4 subsets. So the goal of the set cover problem is to find the smallest collection of sets that cover everything in the ground set. And the same greedy algorithm applies. You pick out the set that has those people in it, E. And then you pick out the set that has the most remaining people in it, T, and so on. And what you end up with is a log n approximation, where n in this case is the number of subsets in the system that you're given. Whereas the stupid algorithm is, there's a version of the stupid algorithm where the approximation ratio turns out to be whatever the size of the largest set is, which could be as big as n. Okay. All right. So that is as much as I want to say about vertex cover. Any other questions about this? If the only thing you remember is the stupid algorithm, that's good, because as I said, this is the best approximation algorithm we know for vertex cover. Okay. Yeah? No, this bound is not tight. In fact, the correct approximation ratio is the nth harmonic number. And that is tight, and it's actually a homework exercise which I'm not assigning this semester, to construct a graph where the greedy algorithm actually constructs a vertex cover of size ox times h of n. N is the number of vertices. Yep. Just the number of vertices. Yeah. Oh, so imagine that. So let me see. I always get this a little bit wrong because there are 2 ways of formulating the problem. So you have a set system where there's a ground set and a collection of subsets of that ground set. Okay. So the right way to think about things, if you want to think about set cover in a graph, is the ground set is a set of edges. And the subsets are all the edges incident to a particular vertex. So when I choose a subset of the edges, they're all incident to a vertex. That's morally the same as just choosing a vertex. Right? There's a dual version called hitting set, where what you want to think is the ground set is the set of vertices, and the sets are the pairs of vertices connected by an edge. But still, you want to choose vertices to everything. So this would be like choosing the minimum number of people in the room so that collectively your last names contain the entire alphabet. And again, you can get a log something approximation. Okay. So let's do something a little bit more, slightly more straightforward. And it's slightly more straightforward because it's really pessimistic. Look at the traveling salesman problem, or TSP. Okay, so what you're given is a graph. Yeah, I can't spell. Graph G vertices and edges. Doesn't actually matter whether this is directed or undirected. Let's just be concrete, say it's an undirected graph. And you're given a weight function that assigns a non-negative real number to every edge in the graph. And what you want to find is the length, actually let me call this not W but L for length, of the shortest Hamiltonian cycle. Right? So this is one of the longest studied NP-hard optimization problems that we know. It's extremely natural because, in part, because this is an actual problem faced by real-world people. In particular, this is a problem, a version of this problem is faced basically every day by every FedEx driver. Which has led to wonderful things like FedEx, I think it's FedEx, maybe UPS. FedEx trucks never turn left because they figured out that the time spent waiting to turn left accumulated over the course of a day was more than the extra time spent turning right 3 times. It's on the order of a 3 or 4% savings, but that's if you're FedEx, that's a few $1 million a day. The story is you should imagine a salesman that has to visit every county seat in Illinois, so under the assumption that they can sell at least one vacuum or one brush or one set of encyclopedias in each city. But they're driving and they want to drive as little as possible. So the graph in that case has as vertices all of the towns that he needs to visit, and as edges the connections, the road connections between them, and the length of those edges is just the length of the road. Now the bad news is that there is no approximation algorithm for this problem, unless P equals NP. And when I say no approximation algorithm, what I actually mean is you pick your favorite function, and I'm going to describe a graph with weights on the edges so that it is NP-hard to compute an f of n approximation of the shortest TSP, where n is whatever number of vertices you want. Okay. Now I'm going to start with the function 2. So I'm just going to show you that there's no 2 approximation. Right. So let's start with a simpler plane. 2 approximate TSP is NP-hard. But you'll see in the end that there's no special properties of 2 used in this proof at all. Okay. So proof I'm going to reduce from the Hamiltonian cycle problem. So here I'm given a graph G with no weights on the edges, and I just want to know whether it has a Hamiltonian cycle or not. Okay, so given this graph G, and I want to know whether it has a Hamiltonian cycle, right? I'm going to reduce it to TSP, but approximate TSP. The graph, I'm going to produce a graph H and a set of edge lengths L, and then I'm going to get some sort of number out, which I'm going to turn into a true or a false. Okay, so H is a complete graph with the same number of vertices as G. And then the length of an edge from U to V is going to be 1 if UV is an edge in G, and 2 otherwise. Actually, yeah, okay. Let's in fact make this a little more interesting. 2n otherwise. Okay, so now notice this new graph that has weighted edges. There are two possibilities for the shortest Hamiltonian cycle in H. H is a complete graph. It has a Hamiltonian cycle. I can write down any permutation of the vertices I want, and that will give me a Hamiltonian path. But the optimal Hamiltonian path, the shortest one, either only uses edges with weight 1, and therefore has total length at most n, or it uses at least one edge of weight bigger than 1, and therefore has total length at least 2n. So the choices are it's at most n, or it's at least 2n, and there's nothing in between. Okay. So there are two cases now. Case 1, if the optimum TSP tour in H has length n, that's going to happen if and only if G is Hamiltonian. That is, G has a Hamiltonian cycle. Right? I take all the edges in the optimum TSP tour, those edges are all in G because they all have weight 1. On the other hand, if the optimum traveling salesman tour in H is size at least 2n, if and only if G is not Hamiltonian, I mean, it does not have a $10 bill. Sorry, it does not have a Hamiltonian cycle. Does not have a Broadway show. And so if I want to distinguish between these two cases, notice that if I had an algorithm that could approximate the optimum traveling salesman tour within a factor of 2, I could distinguish between the case n and 2n. If my approximation is less than 2n, then I know the correct value is n, and I know that the original graph is Hamiltonian. Otherwise, I don't. I think probably to avoid some a couple of boundary cases, maybe I should do that and that. Okay, so I don't have to worry about what happens when my approximation guess is exactly 2n. So if I could guess within a factor of 2 the traveling salesman length of H, then I could distinguish these two cases, and therefore I could tell whether G has a Hamiltonian cycle or not. Now again, no special properties of 2 here. Right? I can erase that 2, I can erase that 2, and I can erase that 2. And I can write in any function I want. Any function at all. And the problem is still hard. Which means there is no hope. Okay. I already know that there's no 0. Well, actually, you know, the approximation ratio has to be greater than 1 no matter what. So, I guess I mean an increasing function, or non-decreasing function. Okay? So, you can't approximate the traveling salesman problem. On the other hand, yes, question?
So is it useful at all to think of an approximation
In terms of L?
in
That's an excellent question. You might ask, for example, if you can get an approximation ratio equal to the ratio of the longest and shortest edge. You don't want to just say the longest edge, because then I can scale everything up to light years. There's really you want to normalize things. And they're possible. But if you just want an approximation ratio expressed strictly in terms of the number of vertices, then you can't do it. Now the funny thing is, if you actually plot all of the county seats in Illinois, or for that matter in the United States, you can go online right now to find the Concord TSP solver. And on this laptop, I can compute provably arbitrarily good approximations by just running it for, I don't know, 20 minutes. So what's going on? In practice, the traveling salesman problem is actually really easy to approximate. And the reason is that in practice, the traveling salesman problem, there's actually some assumptions, some additional assumptions that you can make about the edge weights, which are not going to be true for the examples generated by this particular argument. So in particular, when TSP is most useful is when the underlying lengths define a metric. And in particular, what I want is, that means, I already have, because the graph is undirected, that everything is symmetric. I already have, because all the weights all the edge lengths are positive, that I only get 0 if I try to go from an edge to itself. The thing that I'm missing is something called the triangle inequality, which says that the length of the edge from U to W is at most the length of the edge from U to V plus the length of the edge from V to W. And you'll notice if you look at the example that I've generated up here, this inequality is not going to hold for all triples of vertices U, V, and W in the result in what you get up there, because you might have, for example, 2 edges each of length 1, and then 1 edge with length big, certainly larger than 2, and so the triangle inequality is going to be violated. This is just a simple geometric thing that is satisfied by all actual triangles that you draw on a piece of paper. Okay. So the metric traveling salesman problem assumes this for all vertices U, V, and W. And for the metric traveling salesman problem, there is an efficient approximation. Okay. So in this case, in fact, there's an easy 2 approximation. Okay. So let me throw down the vertices of the graph. I'm not going to draw in the edges because I can assume without loss of generality, really, that all of the edges are there. Some of the edges, I'll use the triangle inequality to fill in the lengths of the edges that wouldn't normally be there, by basically computing shortest paths in advance. Okay, so all of the edges are there, but I'm not going to show them to you for now. So step 1 is I'm going to compute the minimum spanning tree of this edge-weighted graph. Okay. So I don't know. Maybe it looks something like this. Okay. The second step is I'm going to do, well, let me not call it a Euler tour. Let me call it depth first search numbering of the vertices. So I'll start at an arbitrary vertex, say here, and I will label the vertices in order according to some depth first search. So I'll do a depth first search starting at vertex 1. The first time I run into a vertex, I will give it the next label. Okay, so maybe I'll turn down here 4, 5, and then maybe I'll go up here next 6, 7. Okay, and then the third step is we're done. Okay, I've given an ordering for the vertices. Remember, all the edges are there, so that ordering actually specifies a Hamiltonian cycle in the underlying complete graph. Right? So what that Hamiltonian cycle would look like is this in this case. Okay? We know how to compute minimum spanning trees because you saw this in 374, or you saw this in 225, or you read it in my notes. This is something that's easy to do in E log V time, where these number of edges and these number of vertices. So easy small polynomial. And then doing DFS, of course, is easy small polynomial. And so now we're done. Okay. The question is, how do I know that this is a 2 approximation? Well, the way that I'm going to reason about this is by imagining an intermediate step in the way the algorithm works, which is I'm not yet going to put in these arrows. Instead, I'm going to imagine thinking of the tree as a maze. I'm going to walk around keeping my hand on the right-hand wall and going all the way around to the end. Okay. Now, the length of this closed walk in the graph, the length of this is twice the length of the minimum spanning tree. Because I cover every edge of the minimum spanning tree exactly twice. On the other hand, this closed walk visits every vertex in the graph. And therefore, it's at least as long as the shortest closed walk that visits every vertex in the graph, which is the traveling salesman tour. So this length is, on the other hand, at least opt. Okay, so, but that's the wrong direction. That's proving an upper bound on opt. I want to prove a lower bound on opt. So let me take that away for a second. All right, so that means that this tour that I computed over here, the length is at most 2 times the minimum spanning tree. Okay? So the length of the minimum spanning tree is actually going to be the thing that I stick in the middle of the tour that my algorithm computes in the optimum tour. All right, so let me now imagine, I don't know what the optimum tour looks like, but I'll draw a picture where I pretend that I know what it looks like. Just a sec. Okay. Don't need them. So here's a graph, and for the moment, let me imagine that the optimum tour looks like this. Okay. Now, if I remove one of the edges, of the optimal tour, what do I get? What is that pink thing? It's a spanning tree. In fact, it's a spanning path, but fine, it's a spanning tree. And so, on the one hand, this has to be bigger than the minimum spanning tree. But on the other hand, it's also smaller than the optimum because I removed one of the edges. And so my conclusion is that minimum spanning tree is less than or equal to opt. So the tour that I generate with my algorithm is at most twice the minimum spanning tree, and the minimum spanning tree is at most opt. And so that means I have a two approximation algorithm. Okay. Now, this particular heuristic was discovered sometime in, I believe, the early 1960s, and it was the best approximation algorithm known for about 10 years. The more efficient algorithm is something known as the Christofides heuristic, by named after its discoverer who found this in sometime in the late 70s. This is in fact currently the best approximation algorithm known for the traveling salesman tour. I'm just going to show you the algorithm. I don't really have time to walk through the analysis, but if you want, you can see this in the notes. But it starts out the same way as the earlier algorithm. So I'm going to start by computing the minimum spanning tree of the graph. But then the idea is that I want to compute a tour of the graph that's somehow simpler than this tour over here on the right, where I just follow every edge of the minimum spanning tree twice. I want something short based on the minimum spanning tree, but maybe a little bit shorter than what you have here. Now, if you imagine a closed walk that visits every vertex in the graph, you're going to go into every vertex and then back out, and then possibly into the same vertex again and back out. What you're going to end up with, if you trace out all the edges in that closed walk, is every vertex will have even degree. Will be visited, you'll go in and out the same number of times. And so if I want to make this into something that looks like a closed walk, I somehow need to deal with the vertices that have odd degree. Now, in this particular case, this is all the vertices but one. It's not always going to be true. But the interesting thing about the number of vertices in any graph that have odd degree is that there's an even number of them. Because there's the sum of all the degrees is twice the number of edges. So the sum of all the degrees is even. So I can't possibly have an odd number of odd degree vertices. So, so the first step is I'm going to compute a minimum spanning tree. The second is I'm going to compute a minimum cost matching of all of the odd vertices in the minimum spanning tree. So I'm going to figure out the best way to match up the vertices, which may involve duplicating some of the edges in the MST. Now, we've seen already how to compute minimum cost matchings, at least in passing in the homework, when the graph is bipartite. There's a more complicated version of that algorithm that works for arbitrary graphs, whether or not it's bipartite. This is still something that can be done in polynomial time. If nothing else, you could probably write down a linear programming problem for this formulation for this, or at least an integer programming formulation for this problem. Surprisingly, that linear program can be solved in polynomial time, and we'll give you the optimal solution. So there's a more complicated polynomial time algorithm to give you this. This matching M, so the basic argument is, as before, the minimum spanning tree length is at most opt. It turns out that M, the length is at most opt over 2, because if you take every other edge in the traveling salesman tour, it gives you a matching. And then finally, you walk around this graph visiting every edge, do an Euler tour of this graph, you take shortcuts so that you don't visit the same vertex more than once, and you get a tour of length less than the size of that graph. Right, so the punchline is you end up with a 3/2 approximation algorithm. Okay, again, I apologize for having to rush through this. Again, I haven't left out, the only real details I've left out here is how you compute that minimum cost method.
You have to assume that every edge will could exist in this graph.
So I started with the assumption, in fact, this is enforced by having the triangle inequality. Every edge is there.
But if I don't have a loop that that's only construction that I cannot.
Then the triangle inequality is violated. Right, so what you should think of is the edges don't correspond to roads. The edges correspond to travel time. The shortest possible travel time between these two. So you may actually, in terms of the road network, follow the same roads as that are occupied by other edges. But if you think in terms of the abstract graph, with just a single edge without anything. Okay. This is the best known to date. There are some special cases of metric TSP where better things are known, but it's actually a long-standing conjecture that which is worth, yeah, I'd say this is a PhD. There's a long-standing conjecture that you should be able, there should be a 4/3 approximation algorithm for the metric traveling salesman problem. I know not, you're not making any assumptions here other than the triangle. So the conjecture is, in one form, there is a 4/3 approximation, and that is the best you can do. We have a 3/2 upper bound, and we do have a lower bound of 1.1 something. So we don't actually know either the upper or the lower bound is tight. There is an approximation ratio below which it's impossible to go unless p equals NQ. But the conjecture is that the right answer for the approximation ratio that you can get in polynomial time is exactly 4/3. And this has been open for, what is 37 years? So, not what I would recommend as an extra credit problem in homework. In fact, not what I would recommend as a PhD thesis. But a 1.49 approximation algorithm for metric TSP would be a major breakthrough. If you targeted that sort of thing. That's all I want to say about TSP. On Thursday, I will talk about using linear programming to compute approximation algorithms, and in particular to use randomization together with linear programming to do good approximation algorithms. So hopefully this will kind of tie up at least part of the semester into sort of a unified thing. All right, thank you.
这个感觉就是说，上一次我回家的时候。